Uh, if you recall in the last lecture, we derived so the purpose right now is to find out the total energy of a system of electrons which are free, non-interacting, placed inside a magnetic field. In the absence of a magnetic field, we know that the total energy is given by so in the absence of a field, given by dE E G 3D E, where the energy goes from 0 to EF. Correct? It's the total energy of electrons in the absence of a magnetic field. And this turns out to be, after we do all these substitutions, this turns out to be 2 over 5 h bar omega c whole square G3D at the Fermi energy x naught divided by x naught raised to power 5 by 2. ये हमने डिराइव कर लिया इसमें पिछली दफा. ठीक है, so you simply want to put in the value of E. So how do we derive this? So we know that E over h bar omega c is x. So we replace dE by h bar omega c dx. E is given by this. So there's a dE here as well, and there's a G3dE as well. Alright? Where this is three-dimensional density of states, which we've already derived. So after you do all of these calculations, the total energy turns out to be this, in the absence of a magnetic field. Alright. Now let's calculate what happens in the presence of a magnetic field. So in the presence of a magnetic field, we do know that this energy, the Fermi energy, changes. We've already seen the fluctuation in the Fermi energy with respect to the magnetic field, with respect to x naught, which is EF over h bar omega c. So depending upon the Fermi energy and the magnetic field, the Fermi energy in the presence of a magnetic field changes. We've already seen those oscillations. Now if we were to do this calculation, so how do we compute the total energy in the presence of a magnetic field? First of all, you need to construct the integral. The integral now varies from 0 to EF plus some delta EF. So this is the fluctuation in the Fermi energy. Right? So remember, we drew this curve, and I'll show these curves on mathematica as well. So this is our x naught. This is the change in the Fermi energy delta. So you remember, we got curves of this kind. This is 0. So sometimes the Fermi level goes up and sometimes it goes down as x naught changes. Where x naught is EF over h bar omega c. And the reason why this Fermi energy changes is the total density of electrons has to remain constant, whether you have a field or you don't have a field. Right. Now we have to set up an integral dE E G3D in the presence of a magnetic field E. Right? So we set this up. We know what dE is, we know what E is, and we already have an expression for the three-dimensional density of states in the presence of a magnetic field. Now if I were to so this dE gives me h bar omega c dx. This E gives me another h bar omega c, and I also get an x, correct? And this three-dimensional density of states is, as you already know, given by G3D x naught over square root x naught 1/2 x minus L plus half square root, okay? Where we would like to take the sum over all L's, where L is greater than, where L is, x is greater than, this x must be greater than L plus half, or you can apply the Heaviside function. And the integration goes from 0 to, what should I place at the upper limit of the integral? Everything is now in terms of x. What should I have at the upper limit? X naught plus delta x, because the Fermi level has now changed. So I need an x naught plus delta x. Okay, so this is what we need to calculate. And I can put either this condition, or I can put in the Heaviside function. Alright. Now remember that we're taking definite integral. So if the Heaviside function, the step in the Heaviside function is in between the upper and the lower limits, it does not really matter. Now the point is that if I do this calculation, so everything is a constant, it gets out. So G3D x naught 1/2 h bar omega c whole square summation over x, summation over L's, and I'm left with, and there's an L max at the top, dx x minus L plus half. Right? So this is what I really need. I need to compute this integral over here. So this is just an exercise in integration. Nothing kind of serious about it. You just apply integration by parts. Correct? So if I attempt to do this dx x minus L plus half, so this is x minus L plus half 3/2 divided by 3/2 minus dx 2/3 x minus L plus half 3/2. Correct? This is what it might look like. So the next step, I can write this as 2/3 x minus L plus half 3/2 minus 2/3 x minus L plus half, I think 5/2 2/5, okay. Correct. Now I put in the limits. After I do all of this, the final result that I would get is the following. UB is h bar omega c whole square G3D at x naught at the Fermi energy square root x naught. L goes from 0 to some L max. We already know what this L max is, x naught plus delta x plus 2L plus 1 x naught plus delta x minus L plus half. I can put in the Heaviside function if I wish, x naught plus delta x minus L plus half. So this is my total energy in the presence of a magnetic field. Correct? So we need to do this calculation. So now what I would like to plot, I would like to plot this. I would like to see how the total energy changes with, say, the Fermi energy of the magnetic field with respect to x naught. So what I would like to do is, I would like to plot the ratio of the energies. Okay. In fact, I would like to plot how much does the energy change when I apply a magnetic field as a fraction of the total energy in the absence of a magnetic field. And I call this, for convenience, some factor FB. So I really would like to plot UB over U naught minus 1. Let's plot this. This is the fractional change in the energy, total energy in the presence of a magnetic field of this sea of electrons which are not interacting and when they have been subject to a magnetic field. So now I will kind of continually move, shuttle between the blackboard and some graphs. So let me see how, if I'm able to do this properly. Density of states in the absence of field. Then we saw that when we apply a field, the density of states becomes these very high density of states approaching infinity at the Landau levels, followed by a decaying function. Then we overlaid the two graphs, see how the imposition of a magnetic field changes the density of states. From continuous smooth curve, it becomes this corrugated density of states. Then we integrated the density of states. The integration gave us a total number density of electrons. Right? So this is in the absence of a field. And then we imposed a magnetic field and then we zoomed in a little bit. This is what happens in the presence of a magnetic field, the integrated density of fields. And then I zoomed in a bit further and I saw that at certain points the orange curve represents in field integrated density state. So sometimes the number of electrons goes higher for a particular value of x naught. So this is the x naught axis, some Fermi energy in the absence of a magnetic field. So this is some Fermi energy, and this graph is plotted at some magnetic field as well, by the way. So this is EF over h bar omega c. So this is some vertical line. At one vertical line, the number density goes up for a field, and at certain points, certain intervals, it goes below. You can also plot this. So this is the integrated density of states, and that's happening because the Fermi energy itself is shifting up and down. It's going above and below the Fermi energy in the absence of magnetic field. So then we plotted this, and then we kind of focused our attention on the Fermi energy, and we found out what the Fermi energy fluctuation is going to look like as a function of x naught. So for a fixed magnetic field and a fixed Fermi energy, which varies along this axis, so this graph is plotted at a fixed magnetic field, but this axis can be proportional to EF. So the Fermi, this is the zero axis, so the Fermi energy, sometimes it goes below the unperturbed Fermi energy, sometimes it goes above the unperturbed Fermi energy. So if this is my Fermi energy in the absence of a field, for some values of this thing, the Fermi energy in the presence of a field goes down, and for some values it goes up. Okay? this, now I'm going to plot the energies. So now I don't think I was able to do this in the previous lecture, but now what I've done, first row x naught, I've kind of created an array of x naughts. Then for each x naught there is an L max. L max is the highest L for which L plus half is less than x naught. Right? Otherwise the radicand, what's inside the radical sign will become negative. So then I create a table of L maxes, row number 22. Then I have a different an algebraic equation which I solve numerically to find out the change in the Fermi energy. This was from our previous lecture. So XF is my table of all the delta x's, all of these things. X, right? For a given x naught. Remember that delta x is a function of x naught, as we've just seen. So this is xf, delta x is a function of x naught. Then I solve and I find all the delta x's. Then I create this ratio f. Okay, so this is my f. See, this is a minus 1, this is this minus 1, and the rest is the ratio between ub and u naught. Okay, ub is the square root, this square root into this is this thing divided by x naught divided by that thing over there. So square root of here is the denominator. Okay, so this is f. So let's see what this fractional change in the energy looks like upon the imposition of a magnetic field. So this is what it looks like. Now, this doesn't make a lot of sense. I have x naught on the right, so let me zoom in onto this area. This ratio has declined to 0. Let's zoom in on where the interesting stuff happens. Here it is. So now I plotted this function f up to x naught equals 50. So now we see these oscillations riding on top of a decaying envelope of a decaying function. Okay, so this is what this f looks like, and I can zoom in onto some regions to kind of get a clearer view of what's happening. Right? So this is just a zoomed in view between say 10 and 15 of that graph. It's a decaying oscillation. F is a decaying function. It's an oscillation that is riding on a decaying monotonic function. Now I want to calculate the susceptibility of this gas of electrons. Yes, please. Yes. Now this energy ratio that I've defined, I want to find how does it decay. So I need a mechanism of, I need a guess that this function itself is an oscillation riding on top of a monotonic decay. So that monotonic decay, higher the value of x naught, it decays. So I need to find out how does it decay. So what I do is I plot. If I were to plot so what I do next is, let me move to the blackboard. This function of x naught, just like limit doesn't matter. So this function of x naught has some kind of inverse relationship with x naught, some function of x naught. So what I try to presuppose is that this is some constant alpha over x naught, some power here. Could be x naught is for 1, half, square, something. So I kind of presuppose that, suppose this is a square here. So I make a plot between f and 1 over x naught squared. Okay? Forget the oscillation riding on top of it for the time. You're just looking at that kind of monotonic decaying function. Alright? So if I make a plot between f and 1 over x naught squared, if I get a straight line, then this is a good candidate. So now what I've done is I've made a plot between f and 1 over x naught squared, and I get a straight line, a very accurate straight line. Okay, so this is a kind of a semi-symbolic, semi-analytical approach to kind of solve this equation. The analytical approach is kind of more complicated. I can't cover it in class, but I'll refer to some literature for that. So, but this is a nice approach, and it kind of explains the entire machinery of Landau quantization. So now this is a good kind of guess that f is proportional to 1 over x naught squared. I can find alpha. How do I find alpha? I fit this function to a linear model. And when I fit this function to a linear model and fit it, so I get this alpha, which is 0.104. So you get a good estimate of alpha. Alright. So now my f is alpha, which I know what the value of alpha. I know what the value of alpha is. It's 0.1. So my UB U naught alpha over x naught squared plus 1. Right, so this kind of UB over U naught minus alpha is alpha over x naught squared, but this is incomplete because this has not yet captured the oscillations. So now I want to worry about the oscillation as well. In order to, because this is just a map of the monotonic decaying function. Got it? So far so good. Now what I do is you will. Oscillations भी होंगी ना. अच्छा असल में ये देखें ना, ये जो फंक्शन है f, this is not a this is not a function. This is not this function. This is rather a function function which has oscillations riding on top of this. Right? So what we've done, first of all, we take this x naught and fit this baseline without the oscillations, and we notice that this is 1 over x naught squared. Right? So now this f is 1 over x naught squared, but on top of that, you have some other oscillations too. So really your f is alpha over x naught squared 1, which is just this yellow line over here. But on this function, you also have other oscillations. So let's call those oscillations, say, some gx naught. Now this is an oscillatory function. This is also an oscillatory function. Okay, and this oscillatory function represents these small oscillations that ride on top of this decay. Now we want to find out what this gx naught looks like. Right? Correct. So gx naught is now an oscillatory function. The problem is that this gx naught does not have an equal amplitude as you go along. If you observe these curves carefully, this curve, in the beginning, small x naught, the oscillations have large amplitude, and towards the end the oscillations have a smaller amplitude. So the amplitude of the oscillations itself is decaying. So if I want to look at the oscillations themselves, what do? I kind of change this line a little bit. I have f x naught squared over alpha minus 1. I plot this and I call this my oscillation. So now I'm going to make a plot of f that we've already obtained, x naught squared divided by alpha minus 1, and see what the gx's look like. Now this is not going to be a unit amplitude, constant amplitude function, it's going to be decaying function itself. So let's plot this decaying function, this gx naught. So if I were to do that, now I'm finding the decay of the envelope or the oscillations. So this is what the oscillations themselves look like, that are riding on top of the decaying monochrome. Now the oscillations themselves, their amplitude is kind of coming down. So now what I will, I can also zoom in a little bit. Here I zoom in a little bit on some portion of this decay. And then what I do, I kind of predict that the decay of the maxima follows. So x naught goes up, the amplitude decays. So so gx naught will now, gx naught itself, I say that is some beta over x naught raised to power some power here. Could be 1, could be 2, could be half. So if I were to make a plot, assume that this is square root. You don't need to zoom, you can see what works best. You can use half, 1, 3 by 2. So if I put 1/2 here, and if I were to make a plot between g, the g that I have, and 1 over square root of x naught, if I get a straight line, that will give me the value of beta. And it will be linear, this will hold true. So now, therefore now I kind of make a graph between 1 over square root of x naught, right, and g itself. This is what I get, and I get a linear curve. This thing. I should only be looking at the amplitudes. So the amplitudes increase linearly. Okay, and I can test that. So I've written a code that actually tests that. I write a function that detects the peaks of this function. That's what I do. I find the peaks of this oscillatory function. Right? So I find the peaks, and then just to test whether my peak finding routine is working properly, I overlay the peaks and the function q g x naught, which has now been plotted with respect to 1 over square root x naught. And the peaks shown in orange, they overlap with the real peaks of the oscillatory function. So my peak finding function is correct. Now what I simply need to do is I need to fit the peaks to a linear function. That will give me beta.
मैंने वो देखा था कि लीनियरली डिके कर रहा था, एज इन जो ऑसिलेशंस थी वो लीनियरली डिके हो रही थी।
नहीं, वो 1 ओवर स्क्वायर रूट के साथ में डिके हो रही है।
ये वाली चीज़ जो थी,
जो ये पीक्स,
हाँ पीक्स, तो वो नॉन लीनियर डिके है ना। तो यहाँ पे अब
तो मैंने इसको लीनियराइज कर दिया ना, मैंने फिर प्लॉट किया विद रिस्पेक्ट टू 1 ओवर स्क्वायर रूट x नॉट।
ओके,
तो फिर वो लीनियराइज हो जाएगा।
ठीक
ठीक है, then I fit and I get the value of beta, which is 0.5, right? This is a result of fit of the orange peaks, where beta is 0.5. Got it? So now overall, what's the situation that I finally obtained? Let's look at this thing, f of b. F at b is alpha over x naught square 1 plus my gx naught. Now gx naught is now a decaying function. So this is now decay, the decay is beta over x naught with respect to beta over x naught, but then there is some initial amplitude, right? Let's call that simply g bar, some initial amplitude, some constant g bar, and then I also, but the oscillations are still there, but those oscillations are now unit amplitude oscillations. Right? So let's call those oscillations q x naught, where q x naught is simply, this is x naught, and q x naught just unit amplitude oscillations. Yes, please.
So ये जो f of b आपने लिखा है, ये यूनिक फंक्शन होगा, मतलब
यूनिक है,
और कब मतलब ये कि we would not be,
this is the best fit. So this is q x naught, unit amplitude function, because all the amplitude has been subsumed in this g bar, and all the time, this is the oscillatory time variation, this is the monotonic decay. This is non-monotonic, this is oscillatory. So this is the overall f that you get. Now if you observe, if you look at this function here, look at the period of this function. Let's see what the period of this function looks like. But this is with respect to, okay. So, but this is with respect to x, 1 over square root x. So, So we can look at this function. This captures the oscillation already. So the period of this function, say this is 26, this is 27, is 1. So this oscillatory function has a period delta x naught of 1. So this function, this oscillatory function, has a period of 1. And what is delta x naught? This is this is EF h bar omega c. This is the h bar EF over h bar omega c. This is the period of this function. Okay. Omega c is, remember, EB over m. So I can also write EF h bar omega c as, if my EF is constant, h bar omega c is E m b, right? This is the period of this function is 1. This represents the period. Okay, so the difference, so what this really means is that the period of 1 over b. So if I were to plot qx naught as a function for a given Fermi energy as a function of 1 over b. So if on this axis I have 1 over b, and here I plot the oscillatory function qx naught, then this function, this period, will be h bar e over EFn. Right? So if I were to make a plot here, the period of this function when plotted across 1 over b is going to be h bar e EFn. Remember, I have to take an effective mass which is perpendicular to the bright magnetic field. So this is the cyclotron frequency. And this is not the real mass of electron, this is an effective mass of electron inside the band. So some people would like to put an asterisk here. So this is the period of this oscillatory function when plotted with respect to 1 over b. This oscillation, these are quantum oscillations that you see in different properties. And it rises because of the quantization of the Fermi energy, because of the oscillatory nature of the Fermi energy. We've seen that the Fermi energy oscillates. Hence, all other properties that have something to do with the Fermi energy, they also oscillate. Magnetization oscillates, conductivity oscillates, Hall effect oscillates, spin Seebeck effect oscillates, Seebeck effect oscillates, the thermal properties oscillate, and so on. Now, alright, so overall, now what we have is this kind of relationship, and we can now recover from this relationship the total energy of the electrons in the presence of a magnetic field. Now let's try to do that. Any questions? UB is, this is F, UB over U naught, minus 1 is all of this, correct? X naught square plus alpha beta g amplitude qx naught, which is an oscillatory function of period 1 unit amplitude over x naught is for 1/2. Okay, this is what we have, isn't it? this is becomes 5 by 2 square only, 5 by 2. Okay? So UB becomes U naught alpha x naught square. Plus 1. So this becomes U naught plus U naught alpha x naught square plus alpha beta U naught G Q x naught 5 by 2. This is the total energy. You can plot this if you wish. You already know what the values of alpha and beta are. You can also always express U naught in terms of the Fermi energies. So U naught we know is that thing over there. We express this in terms of the Fermi energy. How do we do that? We know that U naught is 3 over 2 n with a G we already know this. We've derived in our previous lecture. We also know that G EF is 3 over 2. 3 over, this is 3 over 5. 3 over 2 n EF. So what we would like to do, we would like to write down this energy in terms of the Fermi energy. Because the Fermi energy is something that we experimentally measure. But we don't like this n over here. So just get this n from here. So this becomes 3 over 5 EF. N is 2 over 3 square GEF. Well, this is 3 dimensional. This is my U naught. Is 2 over 5 EF square G3D EF. Now I can put this U naught in here. Correct? I can also insert it in here. So the energy, the presence of a magnetic field is the unperturbed energy, the absence of a magnetic field plus some deviation. So when you place an object, a quantum mechanical object inside a magnetic field, if the energy changes, that change in energy is due to magnetization. Remember, we already have for a magnetic moment minus mu dot B. But this is the energy of a single magnetic moment. So if you have a large ensemble of moments, the total energy U will be minus M dot into B, where M is now the magnetization. So in order to calculate the magnetization, you can take the derivative of the total energy with respect to B. That derivative will tell you that change in the energy with respect to the magnetic field will give you the magnetization. So if I take this expression and differentiate this with respect to B, I'll get the magnetization. So this is the unperturbed energy in the absolute magnetic field. It does not contribute to the magnetization. But these terms too, because there's an x naught here and an x naught has a b in it, this term also has an x naught. And there's also an x naught in here as well because of the oscillatory nature. Alright? So from this I can calculate the magnetization of this of electrons inside the magnetic field. U naught plus U naught. Now you spell down U naught in this term 2 over 5 EF square G3D at EF alpha over x naught square. Now x naught square is EF square H bar H bar square omega C square. Omega C is E. Alright. So I just write down x naught. I just open up this x naught plus alpha beta U naught. U naught again is 2 over 5 EF square G3D EF G QX naught over X is for 5 by 2 EF 5 by 2 H bar 5 by 2 omega C is E 5 by 2 B 5 by 2 M star 5 by 2. This is an oscillatory function, remember. Now this is my total energy. Okay? Now what I need to do is my M will be minus 2 by 5. This EM square just kind of goes away. Alpha is 0.104. 104. H bar square E square 2B plus an oscillatory term, this term. So I need to differentiate this with respect to B as well. Alright? Now this is so beautiful because I can recognize that my Bohr magneton mu B is EH bar over 2M. This is my definition of my Bohr magneton. So EH bar over M star is 2 mu B. EH bar over M star. So this thing is mu B square. So I'm left with about minus 4 over 5 this 2 multiplied by this 2 and this is 2 mu B square and another 4 mu B square. Okay, B this point 104 plus the oscillatory term. The oscillatory term remains, right? We can't ignore that. That is giving us the oscillations, the magneto oscillations that are really important. Now, if you you have figured all of this out. This is 16 over 5 into 0.1. Right? So this is 1.6 divided by 5. About 0.3. 0.33. It's 1 by 3. Okay? So all of this is minus 1 by 3 mu b square b. Correct? And of course, I can't forget this term here, G 3D EF. This is still there, G 3D EF. G 3D EF. Which is, by the way, 3 over 2 NEF. So the susceptibility is M over H. B is mu naught H, so the susceptibility is minus 1 by 3. And all that is left over here, mu b square, mu naught, G3D EF. If you recall, that's the poly paramagnetism. Ectide, the poly paramagnetic effect. Poly paramagnetism. Remember the spin split bands? You have two kinds of spin. You impose a magnetic field, then those electrons you shift in energy and creates magnetization, a susceptibility which is given by mu b square b 3 over 2 n over EF from our previous lecture, one of our previous lectures. So this susceptibility effect is called Landau susceptibility. This is for free electrons, and it represents, so if you have a sea of free electrons that see a magnetic field, they kind of get a susceptibility. And that susceptibility is related almost the same as poly paramagnetism. Could be smaller by a factor of 1 by 3. But remember that here we're talking about effective masses of electrons as well. So this term, if you do a proper calculation, depends strongly on the effective mass. This term can be bigger, even bigger than the poly paramagnetism if M star is very much different from M, which it is for semiconductors. And look at this minus sign over here. What does this represent? Generally, we've seen in our initial lectures susceptibilities which have a positive sign. Here we're getting a negative sign. What does this show us? So a positive susceptibility, you have H, M. Positive susceptibility like this represents paramagnetism. So you increase H, the M goes up. This is at a particular temperature. This is a paramagnet. A ferromagnet has a similar relationship, but it's non-linear. Okay, but still positive, but very large positive numbers. This is a ferrimagnet or a ferromagnet. Antiferromagnets have no magnetization. And if you get a negative guy, it's called diamagnetism. So you apply a magnetic field. So if I have a diamagnetic object, you apply a magnetic field, H, a magnetization develops inside this object, which is opposite to the applied field. The magnetic field inside the material is reduced. So overall the magnetic field is mu naught H plus M. Alright? So, the field inside the material is mu naught H plus M. But M is now opposite to the magnetic field. So, and this proportionality is chi, the susceptibility. So, this becomes plus chi H. Chi is now negative. So, mu naught H 1 plus chi. If chi is negative, then I can write this as mu naught H. It's negative for diamagnetic material. 1 minus chi bond. Okay? So this is what happens in a diamagnet. The magnetic field decreases inside diamagnet. This factor, mu naught, into this factor is also called the permeability, the relative permeability of this material. So, this is the Landau diamagnetism effect. Whenever you have electrons, free electrons, non-interacting placed inside a magnetic field, they create a negative susceptibility. They create a magnetic field opposite to the applied field. This is also in line with Lenz's law. This also has a classical picture. Now, the only thing is that this quantization is. Let me complete the figures that I've drawn for you, and then we can. I have a few things to describe. So, what I've done is this. What other things that I've done? I've also calculated the ratio of the number densities, and I'll probably give this as homework. So, the ratio of the number densities means that you have no field. You know what the number density is. Now suppose you apply a field. How many electrons are there up till the unperturbed Fermi level? Now the Fermi level, the present field can go up and down. So if the Fermi level has gone down, then more electrons can fill up till the unperturbed Fermi level. If the Fermi level has gone up, fewer electrons now fill up till the unperturbed Fermi level. So I plotted the ratio of n and n naught, right, up till the unperturbed Fermi level. So if I plot this ratio, this is what it really looks like. So this is what all of it looks like. Here. That's zoomed in on a little small region. Now this is a kind of a beautiful, beautiful curve. This is x naught, the Fermi energy. And this is the ratio n over m naught. N in the presence of a magnetic field, n naught in the absence of a magnetic field, where n is the number of electrons that go up till the unperturbed Fermi level. You see, this is the one line. Sometimes this ratio is greater than 1 and sometimes it's less than 1. It's going to be greater than 1 when the Fermi level has gone down in the presence of a magnetic field. Right? So it's instructive to plot this along with the variation in the Fermi energy, so that you can compare the two results. That's what I've done. Next, here. So there is correspondence here. Whenever this is positive, the change is positive, the Fermi level crosses the one, the number ratio crosses the one level. So I've done it, and I think I've done it here. I plotted the two together on one graph. Whenever this crosses the Fermi energy, so this is the Fermi energy in the presence of a magnetic field, and this line represents the Fermi energy in the absence of a magnetic field. Whenever there is a crossing here, this point, this turning point, this turning point, this turning point, the ratio switches from being below 1 to above 1. Really, really nice kind of correspondence. Everything is now working out in perfect symphony with one another. Now, we'll also plot the Fermi energy versus the magnetic field. So far I've been plotting with respect to x naught. X naught is inverse of the magnetic field, right? X naught is proportional to the magnetic field, and it's also proportional to the Fermi energy. So I can also plot directly with respect to the magnetic field. You just have to manipulate the variables a little bit, and that's what I've done over here. This is a plot and another plot. So what I've done over here, I've plotted with respect to 1 over x naught. 1 over x naught is proportional to the magnetic field. 1 over x naught क्या है, h bar omega c ऊपर न्यूमरेटर में आ गया ना. So this is the magnetic field, and here I have the change in Fermi energy. So this is the Fermi energy unperturbed level, this is zero level, and sometimes it goes up and sometimes it goes down. So if I were to make a plot of this, what's really happening, if you want to understand that, go over there. Gaussian diagram. In the absence of a magnetic field, this is our Fermi energy. Now you apply a magnetic field, ignore the small splitting due to the Zeeman effect, due to the spins. You get these Landau levels. L equals 0, L equals 1, and so on. So this is the lowest level, L equals 0. So if this were the case, for the time being, we assume that you apply magnetic field, EF does not change too much. The change is small. Now, when you apply a magnetic field, these levels get spaced further apart. So when one of these levels crosses this Fermi energy, it should really be the Fermi energy in the presence of a magnetic field, but let's assume that delta x is really small. Delta x is small. So when this crosses this Fermi level, because of the dilation of these Landau levels, the density of states at EF spikes. Right? That's what we see. At x naught, at that value of x naught, which is EF over h bar omega c, at that value of x naught is a spike. Whenever EF touches an h bar omega c, Landau level, there is a spike in the density of states. There is a spike in the magnetization, etc. So eventually, if you have a situation in which, suppose the magnetic field is so large that there are only 2 levels, Landau levels, below EF. This is a highly quantum mechanical situation because now you're really in the highly quantized configuration. You're dealing with Landau levels now. You do not have a continuum of states. Remember that in normal circumstances, in normal fields, the number of normal temperature, the number of Landau levels within the Fermi energy goes into the thousands, so you do not see this effect normally. When do you want to see this effect? You want to see this effect when you have these cyclotron orbits, right? The orbital period is omega c. Correct. So you want the time it takes for electron to go around this orbit. You want this t, which is 2 pi over omega c. You want this t to be now there's a scattering time as well, tau. You want the scattering time to be really long. You want this time, in other words, to be smaller than tau. Now tau is the scattering time. Suppose these electrons are seeing phonons, these electrons are seeing magnons, these electrons are seeing impurities in the system. And there is also random thermal motion. Random thermal motion means that electrons are colliding with one another. So there is some mean lifetime for a coherent state. That is represented by tau. This is called the scattering time. You want this scattering time to be much larger than the time it takes for the electron to make one cyclotron orbit, which has a frequency omega c. So you want this condition to be satisfied. So you really want omega c tau to be large. This thing you really want to be larger than 1. Okay? So this is when you will see this Landau quantization. And omega c tau is nothing but EV over m star tau. You want this to be larger than 1. So you really want your magnetic fields to be really, really large. Correct? To see Landau quantization. So you have to have tens of magnetic fields. Normal mortal human beings cannot produce such a magnetic field easily. You need to do very sophisticated experiments. High magnetic field experiments and high magnetic field facilities. Or you want to have the M's really, really small, much smaller than the electron. And that can be achieved in semiconductors. For example, many semiconductors have an electron mass, effective electron mass is just 1% of the mass of the electron. Light holes. In semiconductors there are electrons and there are holes, heavy holes, light holes, all kinds of quasi-particles. M star needs to be really small and the temperature needs to be small because you increase the temperature, tau decreases, the scattering time decreases. So these experiments have to be conducted at very low temperatures. So in this scenario, only 2 levels are occupied. It's possible that the magnetic field is so large that there is only one level below EF. And only that level will be populated. It will have a huge degeneracy. What if the field is raised even further? If the field is raised even further and there are no lower level electrons, generally there are, because this is happening in the conduction band, then there's the valence band as well. Right? There are holes in the valence band. But suppose there's no valence band, then what's going to happen is that this level is going to shift up and EF is also going to shift up. And this is all evident over here. This represents the L equals 0 level. This represents the L equals 1 level. This represents the magnetic quantum limit. This is the purest magnetic Landau level that can be populated. Now, just want 2 more minutes. Lots and lots of things to say, but I just want to show you kind of some results. Now, since anything that depends upon the tensile state of the Fermi energy will give rise to oscillatory behavior. On the top, you have the resistivity of some material. At low temperatures, the oscillations are evident. And this is a plot with respect to B. You can also make a plot with respect to 1 over B. 1 over B will have that period that we've discussed. So the effect is observable at low temperatures and large magnetic fields. Okay. These oscillations in the conductivity, they are called Shubnikov-de Haas oscillations. Here is another plot, and here is yet another plot. So, in the presence of a magnetic field, the resistivity shows oscillatory behavior, or the conductivity shows oscillatory behavior, especially when the fields are large. And it's all because of what we've seen, the Landau quantization phenomenon. Right? So these are Shubnikov-de Haas oscillations. And this is a plot with respect to 1 over B. The separation between these two equally placed points, the period, is going to give us the Fermi energy as well. So this period will give us the Fermi energy or the effective mass. Right? So this is also at different temperatures. You increase the temperatures, these Shobnikov de Haas oscillations diagram. Now, an interesting observation is that if you look at the period over here, just last thing, EF. EF, remember, is, if I modify this, HE, M star, EF is H bar square, KF square, Fermi velocity, 2M star. Now KF square or pi KF square is the area in the K space on the XY plane. So if you have a Fermi surface which is a sphere, Kx, Ky, you have a Fermi sphere and you impose a magnetic field along the z direction. And you observe these oscillations, say in the magnetization, and you observe an oscillatory phenomenon. The period of that oscillation is going to be the area of this circle inside the K plane. Right? This is an extremal circle inside the Fermi sphere. Higher this area, Kf square will be large, the period of oscillation is going to be small. Now in real solids, you never get a nice Fermi sphere, rather you get a very convoluted structure. For example, this is the Fermi sphere for noble metals, gold, silver, platinum, etc. Now you change the direction of the magnetic field, you will get extremal areas for different direction of the magnetic field. For example, if you want to apply a magnetic field which is vertically up, you just have one extremal circle, which is the equatorial plane. But if you apply a magnetic field along one of those small necks, which is a crystallographic direction, 111, which is along the body diagonal of this single crystal, you get two extremal areas. One is a small neck, and the other is the big belly. And if you were to apply the magnetic field along a single crystal along that one plane, that 111 body axis, and you find the oscillations, which are called the de Haas-Van Alphen oscillations, you get a curve of this kind. You get two kinds of periods. One is this period. This period is due to the large extremal area inside that Fermi surface, which is due to the belly of that Fermi surface. This period is due to the neck of the Fermi surface. So you change the orientation of the magnetic field, you can kind of reconstruct the Fermi sphere of electrons inside metals. So this is the whole field of fermiology, in which you kind of reconstruct the Fermi structure. It's like doing forensics on the K space of electrons inside that material. So the period of the oscillations tells you everything. So there's much more to say about Landau quantization. This is also the stepping stone for the quantum Hall effect and many other Nobel Prize winning effects in condensed matter physics. In the next lecture, we'll start a discussion on strongly interacting electrons, the Hubbard model, the tight binding model, and see why ferromagnets even exist. Thank you.